Welcome to the next session of optical communication. So yesterday we had discussed spontaneous emission and stimulated emission. So as you know, as we had discussed, stimulated emissions are the basic principle for lasing action. Unlike the spontaneous emission, which emits incoherent light, which we call it as isotropic radiation, here in stimulated emission, the emitted photon will have the same direction and phase as that of the incident photon, which we call it as coherent radiation. Now let us discuss the principle of laser action. In last class we had discussed a gain medium. So we are creating a gain medium by supplying external energy. In that, so in this, here, this region is acting as the gain region, where the gain medium is supported by stimulated emission. Assume two energy levels E2 and E1, which consists of N2 number of electrons or atoms in the level E2 and N1 number of atoms in the level E1. So in order to, as you know, in order to achieve the sufficient condition, we have to first attain population inversion. So for attaining population inversion, we have to initially excite the atoms from N1 to N2 by supplying external energy. So in the resonant cavity of the laser, say this is a resonant cavity. We had already discussed resonant cavity yesterday. So this is a resonant cavity. So in the resonant cavity of the laser, we are providing a gain medium with E2 and E1 energy levels. So to that medium, when a photon is made to incident, as population inversion had already been achieved due to the incoming photon interaction with the excited atoms in the N2, and provided those atoms doesn't achieve its lifetime, will result in going back to its lower state by emitting multiple photons which are identical in all sense that to the incident one. At the output of the media, at the output of the gain medium, there will be a partially reflecting mirror which will allow some amount of the light to pass through and other part will be reflected back to the gain medium. So some part will be reflected out and other part will get reflected back. This will again improve the gain of the resonant cavity. That means it will assist more and more stimulated emissions. And this process will continue. So now let us see the rate equations associated with lasing action. So as we have discussed just before, N2 is the number of atoms in the higher level, that is E2 level. N1 is the number of atoms in the E1 level. And small n is the incident photon intensity. Then d by dt of N2 is given by minus gamma 2 N2. That is, spontaneous emission is controlled by a factor gamma 2. Spontaneous emission is controlled by a factor gamma 2, which gives or which defines the lifetime of the excited electrons in its higher level. The minus sign indicates that due to this emission, the electrons are back getting back to the lower energy level from the higher energy level. So this is the spontaneous emission. Now, for the stimulated emission, it is controlled by a constant KEM. KEM. And for stimulated absorption, the rate is controlled by K absorption. If this KEM and K absorption are identical or equal, we can say that the stimulated emission and stimulated absorption are occurring in a constant rate, or we can say that there is an equilibrium between stimulated absorption and stimulated emission. So this is we had already discussed. So when N1 is greater than the number of electrons in the or atoms in the lower energy level is greater than the higher level, then as per this equation, as per this one, the net result in the gain region or active region will be absorption. When N1 is greater than N2, inside the active region, the net action will be absorption. So this is an inversion action, right? So most of the inversion in the sense that most of the incoming photons are get absorbed. The loss is high. Now, when N1 is equal to N2, then it is somewhat a transparency. Now, this is a condition for the lasing action, that is population inversion. That is, N2 should always be greater than N1. That means we will obtain a net gain. This we had already discussed when we discussed a resonator. Now let's start discussing more about a semiconductor laser. So you can see various types of semiconductor diodes emitting light: LED, VCSEL, and laser. See, you can see that the spot size of LED is 100 micrometer and core size is 62.5 micrometer. And you know that, see, the spot size is 100 micrometer. We had already discussed in our, while discussing fiber fabrication, the core size is only 8 to 9 micrometers. So coupling of this light, for single mode fiber it is 8 to 9 micrometers, and in the case of multi-mode fiber, the core size is 62.5 or 50 micrometers. So if the spot size, as you can see, the spot size of LED is around 100 micrometer, it is practically very difficult to couple whole light to a single mode fiber when the source is LED, and therefore if we are using this LED always with multi-mode fibers for short distance communication. And in the case of a laser, you can see that the spot size is 10 micrometer. As it is offering a very narrow spot size, this type of source is most commonly used with single mode fiber. Actually, VCSEL, that is a vertical cavity surface emitting laser, is an intermediate between this LED and laser. For short distance communication, presently the LEDs are replaced by this VCSELs. Now the working of a laser. Now you can see the active region is created by a PN junction and it is forward biased. As the forward bias is increasing, we can attain population inversion. So with our prior knowledge, there should be at the two ends there should be reflective end. At one side 100% and other side a partial reflection is required. Now as the photons are entering into this region, that is, this is active region. See, we call this region as active region. Why? Because most of the lasing action, that is the creation of photons, will occur in this region, and therefore this region is termed as the active region. So once a photon get incident on the, or get entering into the active region, those electrons in the higher energy level will get interact with that photon and will result in emission of multiple photons of same nature as that of the incident photon. The figure shows a typical constructional details of a laser. This type of laser follows double heterostructure. See, the main difference between a homostructure and a double heterostructure is that the confinement of electric current as well as optical light is more. We can improve the confinement, light confinement inside the active region, and the electricity or the electric current can be confined more in the strip region, so that we can guide the light perfectly inside the active region. This is active region. So because of this double heterostructure, there is variation. You can see there is a variation in the material construction. It is not the same. So because of this reason, there will be a change in the band gaps due to the drastic or rapid change in the band gap. We can confine the electron flow inside the active region itself, ensuring maximum recombination inside the active region only, so that we can improve the amount of light produced, and this will also increase, and this structure will also help to increase the light confinement inside the active region. But with this structure, there is a chance for lateral spread, and this lateral spread can be reduced by providing high resistivity proton implantation near the strip, either by providing a high resistivity proton implantation near the strip or by creating a PN junction. Either you are providing this high resistive proton implantation or P-type PN junction implantation, both will improve the current confinement and thereby it will reduce the lateral spread.